continuous time signal called energy and power. To motivate the definition of energy of a signal, let's consider a very simple electric circuit where we have a voltage source, and let's call the voltage source as x of t, that is connected to a 1 ohm resistor. So here x of t refers to the voltage waveform that's applied to the circuit. Now at any given time t, the instantaneous power dissipated in the resistor, we know that is going to be the square of the voltage across the resistor divided by the resistance. Right? In this case, the voltage across the resistance at time t is given by x of t. So the square of the voltage is x squared of t divided by the resistance. Of course, in this example, the resistance is just 1 ohm. So this turns out to be equal to x squared of t. So x squared of t is the power that is dissipated at time t, and since x of t is changing with time, the instantaneous power is changing as a function of t. So the total energy that's dissipated in the resistor is given by the integral of the instantaneous power. So that's integral x squared of t dt integrated from negative infinity to positive infinity. Right? So we will define the total energy dissipated in a 1 ohm resistor as the energy of the signal x of t. So using this, we will define the energy in x of t. I will call this as E sub x, and we will define this as the integral from negative infinity to positive infinity of x squared of t dt if x of t is a real signal. But as we have said before, in this class, we are typically interested in a slightly more general framework where x of t could be a complex signal. And in this case, we will define the energy as the square of the magnitude of x of t dt. And indeed, when x of t is real, this will turn out to be exactly the same as x squared of t dt. So that's going to be our definition of the energy of a signal. Now, we started with defining the instantaneous power, right? But the instantaneous power is a function of time. So we can think about the average power that's dissipated in the process of applying x of t to the circuit and ask ourselves, what's the average power that's dissipated in the resistor? To compute the average power, what we could do is this. We could, if you think about x of t, let's say that we have the signal x of t, and I observe the signal over a time window from negative t to positive t. And we could compute the energy of the signal between time negative capital T to positive capital T, and I could take the average of the energy, because the power is the is energy divided by time, right? But the problem is, if I fix my capital T, then depending on what I choose for capital T, I might get different answers for the energy between negative capital T and positive capital T. So what we will do is to define the average power as the limit of the average energy in this time window as capital T becomes large. So we will say that the power in x of t, namely p sub x, will take the limit as t goes to infinity of we take the energy in x of t and we divide that by the time over which we are observing x of t. So this gives us the average energy between time negative t and positive t, and we take the limit of that. We divide that by 2t to get the average power, and then we take the limit of that as t goes to infinity. So these two expressions are going to be our definition of the energy and power of a continuous time signal x of t. Keep in mind that we are in general interested in complex signals, so we should use the magnitude of x of t and square the magnitude. Now, in spite of me saying this many times, I've seen students make mistakes by dropping that magnitude sign. If x of t is complex and if you drop the magnitude sign, then x of t squared itself will be complex and you will end up with some complex quantity for energy. Now, we want as per our definition, energy is what is dissipated in the resistor, so it should really be a real quantity in the end. So if you're computing something for the energy and you get a complex quantity, you want to go back and check your calculations again. And most often it's probably because you forgot to put the magnitude of x of t.